Homework. Put it right there next to Danyan. No, I always kind of, yeah, left, right, top, doesn't really matter. I guess I do them on the left, right? But everyone else does them on the right? I never even noticed.
The book, like, does it one way, but
I don't know. No, it's collaborative.
I don't think there's any sort of, like, agreement on the matter.
Okay, more things. Amen. Just like 7 more things, that's all. There was a packet called Integrals and Riemann sums. That was actually like kind of deep and difficult. Magna, can you write that word? And I would like to go over it. I asked you to do pages like 1 and 2, is that correct?
Yes.
Okay, so I will not, I'm not going to be too pushy about that. But I would like to at least go over a couple of the problems on page 1, because it's actually a little bit hard. Should we do them all, or should we just go right to the one that's like kind of weird?
I think we did the first 2 in class.
I already did the first 2, so there's like not much else on it.
Yeah, let's do number 4. Let's do number 4, because I think it's actually pretty hard. And here's the thing, here's what makes these hard. Eric, there's no like shortcut. You just have to like think, and be smart, and think, and draw a picture, and think about your picture, and then draw a better picture, and then you just know what's going on. So number 4, for example, says take the limit as n goes to infinity of 1 over n times 2 over n squared plus 4 over n squared plus all the way up to 8n over n squared. And what is this basically? Okay. This seems pretty hard. First of all, let's count and figure out how many terms we have, because I feel like that should help us. So how many terms do we have here? Yeah, it seems as if I'm counting by 2s, right? And I eventually end up at 8n. So observation number 1, note that we have 4n terms. Okay, that's important. Otherwise, you can't get the problem right. Okay, the next thing to try to figure out is, it appears as if I am, taking a sample point, plugging it into a function, then taking a new sample point, plugging it into a function, etc., etc. So what does that function appear to be? Yeah, okay, so it appears that the function is f of x equals x squared. And so without further ado, I will draw a picture. And where does it appear that I'm stopping? What is the last x value which I plug into the function? 8. And what's the first thing I plug into the function? 0. So this appears to be sort of a picture of the integral from 0 to 8 of x squared. You guys kind of with me? Oh, that you are. I got that by just observing that, well, I seem to be starting with a number which is very, very, very close to 0. It seems to be the first number I'm plugging into the function, and the last number I'm plugging into the function is basically 8. Is actually exactly 8. Okay, so what would cause me to have this kind of situation? Well, how many subintervals do I have?
4n.
Yeah, this was supposed to be a trivial follow-up to this question, right? If there are 4n things, if there are 4n individual terms being added, then there must be 4n subintervals. Okay, so if there are 4n subintervals, and the total width of the interval is 8, what is delta x, the width of each subinterval? Yeah, it would be the total width, 8, divided by the number of subintervals, which is 4n. So yeah, the answer is 2 over n. And it does appear that I'm skipping by 2 over n every time, so it seems to be good. Okay, so the first number that I would plug into this function would be 2 over n. The next number I'd plug in would be 4 over n, then 6 over n, etc., etc. Eventually I would get to, n over n, which would be 1, picture not to scale, and then just keep on going, and I'd keep going until I got all the way to 8. Follow? Okay, so I have all these rectangles, and now I want to add them all up to find the area under this curve. Well, if I did that, then I would have, you know, the width of the first interval times whatever you get when you plug 2 over n into the squaring function, plus the next one, blah, 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 blah. Everything looks good except there's like one weird problem. What's wrong? We did something like this already. Yeah, Robbie.
It kind of bothers me that the subintervals are 2 over n wide.
What's up?
The two subintervals are seem to be 2 over n wide, and that kind of bothers me.
Oh, it bothers you that
Yeah.
delta x is 2 over n?
Yeah.
Why should that bother you? We did tons of exam problems like that.
Because
Yeah, because the x is 2 over
it feels like the function might not be x squared, basically.
Oh. Ooh.
Like should be x,
Okay, yeah, a simpler way to fix this, although I see what you're saying, kind of. A simpler way to fix this is to just observe that, like, this is wrong, right?
Like 0 to 4.
This should be 2 over n, but it's not. Alice and I talked about this like yesterday, just as the bells were ringing, but I don't think any of the rest of you were paying attention yet. But this number here needs to be 2 over n, right? Because the width of each interval just is 2 over n, and the height is just that. Okay, so how can I fix that problem? Yeah, just multiply by 2. I'm going to multiply by 2, and I'm going to undo the damage with a 1/2. In fact, what we are doing is we are repairing our Riemann sum by basically, like, you know, basically, yeah. This is kind of like doing a, it's like a undo the damage on a Riemann sum level. Okay, so what is this integral then, therefore? This integral is 1/2, or this limit is 1/2 the integral from 0 to 8 of x squared. Go.
Is it possible to do this as an integral from 0 to 4? If you use a different function? Yeah, could you do like quantitative?
Okay, maybe, hold on, let me get an answer here. So the answer here is, what is the answer? What is this? This is like 1/2 times x cubed over 3.
2, right?
So wait, he's trying to tell me, so it's 8 cubed, which is like 2 to the 9th. 512, so 256 over 3, yeah. So the answer to this problem is 256 over 3. Did you guys get that? Or maybe you didn't, but that is the right answer.
What's 8 cubed? Is that 256?
8 cubed is 512, but then we divide by 2.
Oh, yeah.
So Yael says, could we possibly interpret this same Riemann sum as a different function? Maybe, but I don't think so.
If you want the width to be 1 over n instead of 2 over n, because like that's what it looks like.
Right. Then it would have to be 2x. Yeah, that will also work, right? Yeah, it's possible, and I think that will work. It's possible. Where is it? Yeah, it's possible to consider this instead as the function 2x squared. I think, right?
I don't have parentheses around.
But I think you
have
have
to.
to. I think you have. That's right. I think this is
Okay,
right.
that is.
Because now, and so this is like really deep and fascinating and awesome and sort of the point of doing this whole packet. So Yael and sort of Robbie were saying, I'm seeing this not as the function f of x equals x squared. I'm seeing this Riemann sum as representative of the function g equals 2x quantity squared. Well, in that case, then we would go all the way out to 4, and when you plug in 4, you would again get 64, but it would just be a different function. And now, they said they don't need to make this correction factor anymore, because the first thing we plug in is 1 over n. We still have 4 over n terms, but now as I have 4 n terms, but since I'm dividing by a width of 4 now, delta x will just be 1 over n. And then this would be 1 over n, the next number would be 2 over n, the next number would be 3 over n, etc. And if you plug 1 over n into this function, then you get 1 over n comma 2 over n squared, which is the right number to get, right? You guys, is this making sense? I think it's pretty hard. I think it's like maybe the hardest thing like yet. What is this next point? that next point would be 2 over n comma, if you plug 2 over n into this function, you would get 4 over n squared. Following this? And over here, the third guy, if you plug 3 over n in, you get 3 over n comma 6 over n squared. So the pattern's all working. So it turns out that if you do it their way, you get that this same Riemann sum could instead be thought of as just the integral from 0 to 4 of 4x squared. Could that be true? I hope so. This better work. Do you also get 256 over 3? If not, we did something terribly wrong. So this is 4, and then I'll x cubed over 3, 4 to 0, 4 cubed 64. Yeah, it works, right? Whoa, are you impressed? I would be if I were you. This means that the same Riemann sum is interpretable as potentially different integrals, depending on how you look at it. Cool? Whoa. Yeah, Emma's impressed. Yes.
Can't you also do it by just drawing a better picture and seeing that the rectangles?
Right where we're drawing.
Technically, that picture is just actually just wrong.
Oh.
The one with the purple rectangles, but
Yeah.
it's like half the.
Whoa.
Basically, she's saying that the widths are the rectangles.
Yeah.
Yeah. So if you just like do it, if you draw the rectangle so that it's occupying like half of the width of the subinterval,
Yeah.
then you can see that it's just like half of the area.
Oh, that's kind of interesting. Eob wants, this has like never been done before. Eob wants to say that the first rectangle, that the first way of thinking about it could be what you're actually just doing in a strange twist is you're going through, you're splitting up the function into subintervals, but you're only taking half of the rectangle on each subinterval. Yeah, okay. So then it would be half the integral from 0 to 8 of x squared. I accept. Yeah, cool. So it's kind of more it's a more geometric solution to this as opposed to the more algebraic way I did it. So yeah, I like it. Okay, should we do like one more, like on page 2, or actually I think we're good. I feel like we're good. Are we good? All right, good. Let's do something else. Oh, 5. Unfortunately, you don't know how to do this yet. Did you get the integral from?
Yes, we.
Did you get, no, not exactly. Did you get the integral from 0 to 1 of 1 over x squared dx?
Yeah.
You got that far? If you got that far, good, stop. Next year you'll learn how to do integrals like this. Because what makes this integral sort of different than any other integral we've seen before?
Oh yeah.
It doesn't exist at
I'm not going to claim whether it exists or doesn't exist, but you should be skeptical that it exists. Because there's like, you know, there's like, yeah. Infinite action going on. Oh yeah, that should be like 1, right? So when I plug in 1, I get 1, but up here, doing like, going very high.
Doesn't it like have a width of 0? Then like it's
Yeah, so like if you do LRAM, you're gonna have one really big rectangle there on the left. So that should,
That's another.
that should be a cause for concern. So you should, maybe this is the wrong face. Maybe the face should be, how do you do scared?
That's not fair.
I need to learn my, like, I need to take a smiley face class. Alright, good.
Yeah. Do an O for mouth.
Yeah.
Everyone has a different scared face.
No.
Yeah.
Like,
I don't.
like that? Oh yeah.
Like a.
Or like do like a.
I learned so many things to learn from teenagers. Alright. How come you guys never taught me anything useful, like Pearl or something, or I don't know. Whatever.
Pearl's like hard. Like
Yeah, or whatever.
Pearl's
Something
not
that can
fun.
give each
There's
other.
a poem. There's a poem written in Pearl.
There's
Alright,
many
good.
poems written in Pearl.
Alright, good.
Compiling
So,
Pearl can't be done.
let's move on. Kendall, do you feel like you can handle this packet now? Does this help?
Put it in your Pearl code.
Okay, it gets a little harder. I feel like the awesomest question ever is like 10, because those can be naturally done in multiple different ways. So we're talking more about that later. But for now, let's do one of the other 19 things that you're going to do this period.
Wait, second,
One
seven
is,
rows. Set 7.
You lied to us.
yeah.
Down to 6.
Oh. Can you give it back to me?
Excited.
Another packet?
Yeah.
But like, it can't, wait, hold up, Steve. It goes like this. How's it make?
No.
So I don't think it's like one. I like got that too, but I was like, what's that?
Okay, the fundamental theorem of calculus is really important, and for that reason it features prominently on the AP exam. Every single year on the AP exam, they always have a question that's more or less just, hey man, do you understand the fundamental theorem of calculus? So I have prepared a packet, which is 4 problems, all of which are old AP problems, and so we are going to do these problems, one, to make sure that we do understand the FTC, but also to practice the kind of weird questions that they ask about, because we just are. Okay, let's see, what should we do? Let's do do you have a preference? Let's do the one on page 2. Yeah, that seems kind of hard. So flip to page 2, and on page 2 you will see classic calculus problem. Actually, can you flip the camera? We're going to do it here. You will see a picture. Everyone, take a minute and read this page 2, and then we're going to do this problem together, and it's going to take 5 minutes.
Oh, this is a classic calculus. What? Oh, it's supposed to be funny. Hey.
This is f prime. In other words, we are looking at the derivative of a function. This function is defined on the interval from -5 to 5 only. And they also tell you a tiny little thing which they squeeze in, you couldn't miss it, but is actually very important, that f of 1 is 3. The graph of f prime, the derivative of f, consists of 2 semicircles and 2 line segments shown above. Okay, so, and here's the thing. I respect all kinds of interesting and creative thinking, but when it comes down to writing the answer, there's like pretty much only one way to do it correctly. And we're not going to talk about like upside down rectangles and backwards rectangles and stuff like that. We're going to just like do it for real. Right. Also, yeah. Also, don't talk about the elephants. So where does f have a relative min? F. Except it says max. Where does f have a relative max? Justify your answer. Okay, the way to do this, if I'm just going to tell you, because it's just whatever. We'll do one and then you'll do the other 3 by yourself. Pretty much, exactly, yeah. What you need to do, in order to know when a function has a relative max, temporarily just forget about all this crap and just be like, hey man, when does a function have a relative max in general? When what goes from positive to negative? Yes, f has a relative max when f prime goes from positive to negative. Do you see anywhere where f prime goes from positive to negative?
Yes.
Negative 3 and 4. Yup. That's all you write. Answer. At x equals -3 and at x equals 4. And the reason, because f prime changes from positive to negative. That's it.
You don't have to.
By the first derivative test, yeah. You could, I mean, I like you to write that, but you're not going to take off. You're all right. Okay. Okay, cool. Where do we have a point of inflection? Well, one weird thing is that actually every sort of teacher in every calculus textbook defines point of inflection slightly differently. So many different answers will be considered acceptable here. But loosely speaking, how do we do it in our class? When do you have a point of inflection?
When the
The derivative changes, increasing and decreasing.
Yeah, I got 3 different answers and they're all correct. One way to think about a point of inflection is the place where concavity changes. Another way to think of it, therefore, is saying where the derivative goes from increasing to decreasing, or the derivative goes from decreasing to increasing. It's also equivalent to say where the second derivative changes sign. Any one of those would be acceptable. So where is that happening? -4, -1,
It's like whether the slope is way up.
and 2. I think those are the answers, right? Yeah, it's a very abstract problem, which makes it kind of weird. So, but this is happening at -4, -1, and 2. Why? Because if you think about what's going on at -4, well, this is f prime. So f double prime, this is how I think of it, f double prime is positive, but then negative. In other words, the second derivative is changing sign until you have a point of inflection. I think our textbook actually defines point of inflection as a place where the derivative goes from increasing to decreasing. Is that how our book does it? You know, who knows? All right, yeah, so here, and justify your answer. Okay, so I guess we could do them one at a time. Is that what I did? Well, okay. Because in each case, f prime changes from increasing to decreasing or decreasing to increasing. Are we okay with that? Danyam, are we okay? Yeah. Find all intervals on which the graph of f is concave up and also has positive slope. Take a minute to think about that.
Yeah, that's my favorite question.
Alright, so we just need to translate that into, there's a bunch of different ways to do this, but we need to kind of translate that into language which is easy to evaluate. So if the function is concave up, then that means that the second derivative is positive, or the first derivative is increasing. Same thing. So we want to know where f prime is increasing, is equivalent to saying where f double prime is positive, is equivalent to saying where f is concave up, yeah? And it also must be true that f has positive slope, which is just another way of saying f prime is positive. So I'm rephrasing it in terms of f prime because f prime happens to be the thing whose graph they're just giving me. In other words, I need to find, if I'm looking for where it's concave up and with positive slope, then I just need to look at the graph of f prime and figure out on what intervals is it positive and increasing. Answer? Yeah, on the interval from -5 to -4, and on the interval from 1 to 2. Yep. That's good enough with me. Does anyone like make a whole like sign chart and compare them? Some people might find that kind of helpful. I mean, Kendall do that? Yeah. So you could, that's another thing that some people do. They say, all right, well let's look at f prime on the whole interval from -5 to 5. It's not necessary, but it's something we could potentially do. And here's 1, and then here's like -3, right? So just by inspection, f prime is positive, then it's negative, then it's positive, and then it's negative. And then we could look at f double prime. Well, f double prime is the derivative of that. Well, it's increased. F double is going to be positive, then it's going to be negative until -1, right? And then it's going to be positive until 2. And then negative until 5. Do you guys see where I got those numbers from? Just from whether f prime is increasing or decreasing. And just compare the number lines for places where they're both positive, and we get the same thing that way. So like, all right, a little bit more thorough maybe. Okay, part D I feel like is the hard one. It's maybe not so hard to figure out the answer, but it's difficult to justify. Find the absolute minimum, explain your reasoning. Okay, the thing to do is to, oh my god, but you should practice. You should be practicing the process of like justifying your answer and explaining your reason. That's kind of what we're doing. We're not really going through, whether you can figure out the answer is like 50%. It's also can you write with like a complete sentence, like why it's true. So I'm being explicit in class right now about what's expected of you, so you should like do that.
What? Wait,
Yeah, good.
say it again?
I'm just trying to like get you all to like learn like the way when they says justify, they're serious. They're not just you can't just write yeah because like I said so. You have to like write real like words and stuff.
So
you're gonna be able to do that at some point?
Yes.
Okay. All right.
No.
Team Junior
Wait, so
Slack.
like, what exactly
What's up?
is
I am not a
like
slacker.
justify like you write?
Like what we've been doing. Like what we've been doing. Okay. What's up? No, you don't have to. But if it helps you, go for it. Okay. Last part. How do you find the absolute minimum of a function in general?
Find the relative.
Laura.
Find the relative mins, and then you also find the endpoints and compare the values.
Yeah. Endpoints, relative minima. That's really what it comes down to, right? If we want the absolute minimum, we need to check the endpoints, and then we need to look at the critical points, and then we need to test them all. That's pretty much it, right? Okay, so let's test the endpoints. We need to compute what is f of, for example, 5. So what is f of 5?
That's F.
I think
We don't know.
We have no
we need
idea.
to.
We don't know.
Or do it. Yeah, there's one thing that I mentioned as being important that drew your attention to it, which has not come up yet.
F of 1 equals 3.
F of 1 is 3. Why? How is that relevant to computing what f of 5 is? This is like real calculus we're doing now. In fact, if you understand FTC Part 2, then you should understand what's going on. In fact, I'm just realizing that there's this worksheet I should have done before, which would have been better. Emma or someone, Emma.
So you know like the slope of everything else relative, so I guess you can just like calculate it instead.
Yeah, that's a slightly lame way of doing it though, but I agree. At 1, I know that the function is 3. By how much does the function change from 1 to 5?
It's like,
Oh, wait, right there.
Yeah, that's what the integral is, right? That's actually that's what an integral is. An integral is the net change. So the f of 5 is literally f of 1 plus, it's just what the integral means. The integral is the net change. So the integral from 1 to 5 of f prime, right? The integral from 1 to 5 f prime is the change in f from 1 to 5.
Wait, I missed it.
Hold on. Just think about it this way. Think about it this way. Just like off to the side. If I'm just like, yo, people who have been paying attention, what is the integral from 1 to 5 of f prime of x dx? The fundamental theorem of calculus is what tells me that this is f of 5 minus f of 1.
Oh! Okay, see.
This is
Now I get it.
This
I
is
was like,
FTC2. Sometimes it's referred to as the net change theorem or something like that, right? It says that the integral of the rate at which something changes is the net change.
Brought it over.
Kind of with me on this?
Yeah.
So thus you should sort of begin in your brain to think of it as f of 5 is f of 1 plus
Oh, because like my.
by how much f changes from 1 to 5, which is just what the integral is. Follow? Oh yeah, good. Good, learning's happening. So f of 1 is 3, and then you just do an interval. What's the interval from 1 to 5? You just look at it and do it, yeah. I think it's like 3 halves, right?
3 halves?
Is it 3 halves? No, I'm sorry, I messed up. It's 3 times 3 minus a half. 2 and a half. Wait, what did I just do wrong? That's right, 6, 3, yeah, 2 and a half, 5 halves.
5 halves.
Yes. Boom. Final answer, 11 halves. Accept?
So that's all you need, right?
That's all you need to write for that part, yeah. Okay, what's f of negative 5? All right, this is a little bit harder. And your instinct is probably not to do what I'm about to do, but what I'm about to do is really cool. Well, okay, actually, do it your own way. Well, how should we compute f of negative 5?
F of 1 plus
Oh wait, yeah, they're the same.
Yeah, one thing you could do is just literally the exact same thing. You could just be like, f of negative 5 is just f of 1 plus the integral from 1 to negative 5. And this is actually a sort of way in which it's sort of useful to sometimes do integrals backwards, right? Because literally, like, the integral from 1 to negative 5 represents the change in f from 1 to negative 5. If it makes you feel better to write it as f of 1 minus the integral from negative 5 to 1, well then that's great too, because that's the same thing, right? You're taking the amount at which the functions change. Does this second line make more sense? Or it should make equal amount of sense, right? That the integral from negative 5 to 1 is the amount the function changes from negative 5 to 1. So if you take that away from f of 1, then you should be back where you started f of negative 5. And actually, if you move that over and move that over, it's algebraically like the same thing. Okay, so again, you just do it. What is f of negative 5? It's 3 minus, and then math happens. What is that? 1. It's like a half of a little circle, so it's like a pi over 2, and a 2 pi? 2 pi. So I get that f of negative 5 is, oh, oops, so that should be minus. Sorry. Yeah. So it's a half of a pi circle, and it's a half of a 4 pi circle, but upside down, and then being subtracted. Oh man. So it's 3 plus 3 pi over 2. A lot of things to get right there. Agreed? Okay. So who's with me? Most people, hopefully? Okay. I looked up, I saw no one. All right. So f of 5 is 11 halves. F of negative 5 is 3 plus 3 pi over 2. All right, so far all we've done is find endpoints, nothing else. So now we need to find relative minima and compare. Where is the only relative, or where are the relative minima? I think just one, right? Because f has a relative minimum where f prime goes from negative to positive.
Yeah.
So I can now have to write something